Good evening, dear all. This is my last theory video for the chapter number 1 of class 12. I have recorded various topics of this chapter and have uploaded in my YouTube channel Physics with Dhanu Saraiya. Please subscribe the channel and see all the topics and the videos one by one so that you understand the concept very clearly. So today we are doing the last topic, that is field due to a uniformly charged thin spherical shell using Gauss's law application. Okay, now here as usual, let us first describe what is uniformly charged. Uniformly charged means this particular shell has equal charge density at every section of the shell. Okay, and when we are saying thin spherical shell, the word shell here means a hollow sphere, just like a plastic ball. Now we want to find out the electric field due to the plastic ball, that is the spherical shell which is thin, at a point outside the shell, at a point on the shell, and at a point inside the shell. So we will consider three different points. Outside the shell, already seen here P, the point P is outside the shell. Then we will consider a point P on the shell. Then we will consider a point P inside the shell. So we will consider the cases separately. Right now we will start with field outside the shell. Now whenever there is a question with a diagram, your eyes should go on the diagram what is given. Whether in the CBSE or whether in the JEE NEET, your eyes must go to diagram and understand the diagram. For that, while learning itself, you should understand what are the different parts of the diagram. Okay, and what are the variables given there. Fine. So first let us consider this particular shell which is shown blue in color. This is the diagram from the textbook. Every diagram from the textbook is a question in itself. So learn the diagram from the textbook very carefully. Okay, then on that variations can be done. Fine. So this is a shell with a radius r, as you can see, which is uniformly charged. So the charge always resides on the surface of the shell, and this particular shell has a surface area S as shown here, and we have taken a point P outside the shell, and through this point P we have drawn a circular Gaussian surface. Okay, and this particular shell has a surface charge density of sigma. So in brief, let us just write what it is. Okay, what are these variables given to us? Capital R, radius of the shell which we have taken. Small r is the radius of the Gaussian surface which is passing through the point P. I'm just writing in short. And O is the center. S is the surface area of shell given by 4 pi r square. Similarly, S1 is the surface area of the Gaussian spherical shell surface given by 4 pi r square because its radius is small r. Then we have sigma, surface charge density. Sigma is equal to, according to the definition, Q upon the surface area, that is 4 pi r square of the shell itself. That's why Q is equal to sigma 4 pi r square. In the whole derivation, in the whole concept, we shall be using the formula of sigma and the formula of Q also. Fine. So this is the description of the diagram in short. Now, as usual, in this derivation also we shall consider two flux formulas which we have already learnt. One, phi is equal to E delta S, or S also we can write by definition of flux. 2, phi is equal to Q upon epsilon naught by the Gauss's law theorem, or simply you can say Gauss's law. We shall consider these two formulas to derive the electric field outside the shell, for a point outside the shell. So let us do that by these two formulas. Okay, now first let me write down the flux phi 1 for the Gaussian surface using the formula 1. So phi 1 is equal to E arrow dot. For the Gaussian surface, S1 is the surface area, so I shall write S1. Clear? Okay. Fine. So I can write ES1 cos theta, where theta is the angle between E and S1. Going to the diagram, what will be the angle between the electric field, say from this charge radially outwards, just you can imagine here, and then radially outwards, correct? So this is the diagram, or this is the direction of the electric field for any charge. You can go radially outwards, fine? And for this particular portion of surface area of the Gaussian surface, let us draw the direction of S1 or delta S1. Okay, that is also same. Why it is the same? Reason, the direction of the area element is taken perpendicular outwards. So if I consider this as the tangent here for the circular portion, then this is normal to the tangent. So S1 and E both are in the same direction. So theta is equal to 0, which I will substitute here and write is equal to 1. Why? Because cos 0 is 1. So finally I have phi 1 is equal to E S1. S1 I can substitute from there. So I can write E 4 pi r square. Let me name this as equation number 3. 1 and 2 I have already named. Now let me find out phi 2 using the equation 2 for the Gauss's law, such that Q is the charge enclosed by the Gaussian surface. So Q is the charge enclosed by the Gaussian surface. That's why I am using the formula number 2 upon epsilon naught. From the formula there, we can write Q is equal to sigma 4 pi r square upon epsilon naught. Let me name this as equation 4. Fine. Now, phi 1 and phi 2 both are the fluxes through the given shell or for the given shell. So I can equate them. Fine. So let me equate phi 1 and phi 2. So that I get E 4 pi r square is equal to sigma 4 pi capital R square upon epsilon naught I can cancel 4 pi on both the sides so that I get E is equal to sigma r square. Bringing small r square down, I get epsilon naught r square. So this gives me the formula of electric field for a point outside the shell with given sigma, radius r for the shell, and small r is the distance between the point and the center of the shell. Epsilon naught is known to us. So this is the formula if it is asked as a formula. Now from here we can further extend this formula to the board question asked or JEE or NEET question asked to show another electric field formula such that you will feel or it is understood that the charge on the cell, the charge on the shell, surface of the shell is behaving as if all the charge is concentrated at the center. It is only behaving. Charge is on the surface of the shell. But the behavior or the formula will show as if all this charge together is concentrated at the center O. For that, let us find out the formula. Fine? So that we correlate with what we are speaking. Fine? So let us correlate with what we are speaking. And here I have sigma. As I said, we will use those formulas. So from there, let me use the formula for sigma in this particular equation. So what do I get? E is equal to Q upon 4 pi r square as it is from here, epsilon naught as it is from denominator, and r square is also as it is from the denominator of the equation number 5. Let us name it as equation number 5. So what can I cancel here? I can cancel r square and r square. So what am I left out with? E is equal to Q upon 4 pi epsilon naught r square, which can be written as K, Q upon r square also, which formula resembles exactly for the electric field formula which we have derived in the beginning of the chapter for a single charge Q. We can continue this equation as E is equal to KQ upon R square, which shows us that as if all the charge on the shell is concentrated at the center and the value of the charge is Q, such that its formula of the electric field is KQ upon R square, which was the original formula which we have derived early in the chapter. Fine. Now what about the direction? We can just put an arrow here. We can put an r cap here. R cap is the unit vector which will decide or which will tell us the direction of the electric field. As usual, if sigma is greater than 0, then we have radially outwards. The direction of r cap is radially outwards. Okay, and if sigma is less than 0, then radially inwards. Now remember, this question can also be asked with one more mathematical expression without saying field outside the shell. It can be simply asked with r greater than r. Here also we can write r greater than r. What does this mean? That the point is outside the shell. R greater than r, that means this distance r from the center to the point is greater than the radius of the shell itself. Okay, so without writing the whole sentence, find an electric field for a point outside the shell. It can be just written as for r greater than r. Clear? That also can be given to you as a question. Clear? So remember this particular mathematical inequality when small r is greater than r for this type of derivation. Okay. Now, what if the point is on the shell? So another mathematical expression we can write r is equal to r in the same formula. Fine. So what do we write? What do we get? E is equal to K Q upon, instead of small r, I will write capital R. So what will I get? Capital R square. I can even write K, not K. I can even write Q upon 4 pi epsilon naught. Instead of K, I have put 1 upon epsilon naught R square. What is this condition? When our point is on the shell. Fine. Okay. So this also we can write. Now there is one more type of mathematical expression which can be derived from here. For the electric field for a point on the shell, on the surface of the shell. Let us again put Q is equal to sigma 4 pi r square from that equation. So what we will get? E is equal to, what is our sigma there? What is our Q there? Sigma 4 pi r square. I have written Q as sigma 4 pi r square. 4 pi epsilon naught r square. I am rewriting the denominator. I can cut 4 pi, 4 pi. I can cut r square, r square. So what do I get? I get sigma upon epsilon naught. So this is another formula for the electric field with sigma as surface charge density for a point P on the shell itself. Fine? Clear? Okay. So these are the formulas. I rewrite them separately so that for the particular variation you remember the formula. These two are the formulas for the electric field when r is greater than r. What do we write here? E is equal to Q upon 4 pi epsilon naught r square for r equal to r, or E is equal to sigma upon epsilon naught also for r is equal to r, such that the point which we are considering is on the shell. So we have completed two sections. One is for a point outside the shell. Second one, point on the shell. Now let us go to the third section where the point which we are considering is inside the shell. Fine. So let us go to that. For that I have used another page and the diagram is available to us. Let us again understand the diagram. We have a shell. This is also a textbook diagram. We have a shell and that shell has a radius capital R. Point which we are considering P is inside the shell. And what is the distance of O to P, center to P? Small r. Using the formulas which we have used just now, what we have used? Phi is equal to E dot delta S. Phi is equal to Q upon epsilon naught. Using these two formulas, again we will get the electric field for a point inside the shell. Correct? Let us name this as equation 1. Let us name this as equation number 2. We shall follow the same process. So, with the same logic, let us find out phi 1 for the Gaussian surface inside the shell, which is also circular in the shape. Okay, so E, as written previously, this is S1, that is the surface area of the Gaussian surface. S, surface area of the shell itself. Let us write what is S1 and what is S. S is equal to 4 pi r square of the shell. S1 is equal to 4 pi r square of the Gaussian surface. This is of the shell. The other one will be of the Gaussian surface. Okay. So now I will write here E arrow, S arrow. With the same argument it becomes ES. Reason, theta is equal to 0. Needless to draw, but we can draw also. There is no issue. Okay. So here we have E arrow. And same direction is S1 also. So theta is equal to 0 degree. If theta is equal to 0 degree, then cos 0 is 1. So we get phi is equal to ES. Cos 0 is 1, ES1. What is ES1? 4 pi r square. Now for the Gaussian surface, let us name this as phi 1. Or for the Gauss's law, Q is the charge enclosed by the Gaussian surface. Is there any charge enclosed by the Gaussian surface? Where is the charge? The charge is on the surface. There is no charge inside the shell. There is no charge enclosed by the Gaussian surface. So what is Q? What is Q net in this case? Q net is equal to 0. So here I get 0 upon epsilon naught, so 0. Okay, so equating 3 and 4, we get 3 is equal to 4. What do we get? Phi 1 is equal to phi 2. So we write E 4 pi r square from equation 3 is equal to 0 from equation 4. Therefore, we get E is equal to 0. So remember, for a thin spherical shell, inside the shell, the electric field is 0. Understood? Okay, I hope I am clear that inside the shell, if we have a point, the electric field is 0. Fine. So we have done 3 sections. Section 1, point outside this shell. Section 2, point on the shell. Section 3, point inside the shell. Let us write down all the 3 electric fields together and hence draw a graph between E and the distance of the point from the center. Fine. Okay. So let us first write down first section. What did we get? E is equal to K Q upon R square, where R is the distance between the shell, between the center of the shell and the point P. This is our first equation. That means E, what does this mean? E is inversely proportional to R square. Point 2, where this was for R greater than R. R increases, E decreases. It is understood. Now, this is for the first condition. Now, for the second condition, R is equal to R. What do we get? We get the same equation, K Q upon capital R square this time. This value of R is fixed because we have taken that shell. of radius r. So it is constant value. And it is a maximum value also. So I can write Emax. After this, r is going to increase. Distance is going to increase from the shell. So E is going to decrease. So Emax for r is equal to r is maximum. Remember, all these are small points. These are all your NEET and JEE and CBSE, whatever entrances you write. So the moment you see this condition r greater than r, E is inversely proportional to r square. The moment you see r is equal to r, E is equal to kq upon r square, which is a fixed point or which is a fixed value, constant value, and it is maximum also. Next condition, r less than r, that is the point is inside the shell. What did I get? E is equal to 0. Okay. So considering these three conditions, that is r greater than r is equal to r less than r, let us plot a graph. Okay, so let us plot a graph between E and R. Okay, and let us divide the graph into three sections where R is less than R, that means the point is inside the shell, R is equal to R, that is the point is on the surface of the shell, and R greater than R where the point is outside the shell. For R less than R, what did we get? E is equal to 0, so there are no points. Fine, I cannot draw any graph. For R is equal to R, maximum value, this is my point. Okay, Emax, let me write. And for R greater than R, okay, for R greater than R, E is inversely proportional to R square. So how do I draw the graph? I draw the graph negative curve. Fine. So sometimes just by giving this graph, also the question can be asked. The application can be asked. Which application this kind of graph we will get? For a thin spherical shell. Now, other than this word thin spherical shell, one more word can be used, hollow sphere. Whether hollow sphere or thin spherical shell, both are same. Hollow, there is no material inside. It is a shell. Clear? Okay. So, I hope I am clear with the whole topic of finding electric field due to or at a point for a thin spherical shell, in which we considered all the three cases, r greater than r equal to r less than r, found out the equations. Other than these three equations also there are equations, remember them also, and we have drawn the graph also. Clear? I hope you have understood this section very clearly. In the next video for different topics, I shall do the numericals. Already for a few topics, what kind of numericals can be done for this particular concept, that video I have already shared with you. Fine. Now rest topics which are left out, we shall do the numericals with the concept. Clear? Okay. Do follow and do subscribe my channel Physics with Dhanu Saraiya. I shall complete my syllabus one by one video, topic wise. Remember that. Okay. I just move and you please take a screenshot.